Type one wrong character into a running program, and the most code dies with a wall of red text. Python lets you catch that failure, name it, respond to it, and even crash again on your own terms. The difference between a blunt shield and a precision instrument is knowing exactly which exception you caught. The classic place for a try and except block is around user input, because users are unpredictable. You can print the clearest instructions imaginable, tell me one number, then tell me another number, and you still have no control over what gets typed. A careful user follows directions. Everyone else types words, blank lines, or zeros. Defensive code assumes the worst and prepares a plan for it. Here is the naive version, 3 lines. We ask for one number and convert the input to an integer, storing it in the variable a. We ask for another number and store it in b. Then we print a divided by b. A cooperative user types the numerals 5 and 8, both conversions succeed, and Python prints 0.625. As long as everyone follows directions, this little program is flawless. Now a user tries to be funny and types the word 5, letters, not the numeral. The conversion to an integer has no idea what to do with letters, so it raises a value error and the program crashes with the cryptic invalid literal message. Another user enters 0 for the second number. Both conversions succeed, but the division fails because Python cannot divide by 0, so it raises a zero division error. 2 different users, 2 different exceptions, one dead program either way. The risky lines are known, so we wrap them in a try block and attach a bare except. Proper input still works exactly as before, but now, when someone types letters, the value error is caught, and the program prints the message bug in user input. When someone enters 0, the zero division error is caught, and the very same friendly message appears. No red wall of text, no crash. The program ends politely instead of blowing up in the user's face. There is a cost to that politeness. Typing letters and dividing by 0 are very different mistakes, yet both users see the same generic message. One user never gave us numbers at all. The other gave us 2 perfectly good integers, and only the division failed. A single catch-all cannot tell those situations apart, so it cannot respond differently. We want each anticipated error to get its own recovery plan. Python lets one try block carry several except blocks, each naming the exception it handles. The try block now prints both a divided by b and a plus b. The first handler names value error. If a conversion fails, we print could not convert to a number, so the user knows exactly what went wrong. The second handler names zero division error, and it does more than apologize. It flags the problem by printing can't divide by 0, declares that a divided by b is instead infinity, and then still prints a plus b, because adding 0 to a is no problem. The final bear except sits last, a catch-all for anything we failed to anticipate. Python runs only the block matching the exception that was raised. First run, a perfectly cooperative user types 5 and 8. Every line inside the try block executes. The program prints a divided by b equals 0.625, then a plus b equals 13, and none of the except blocks run at all. Handlers cost nothing until an exception fires. Second run, the user types a letter. The very first conversion raises a value error. Python abandons the rest of the try block, and the user sees could not convert to a number, a graceful ending that names the mistake. Third run, the variable a gets 6 and b gets 0. Both conversions succeed, but the division raises a zero division error, and that handler takes over. It prints can't divide by 0, then instead, a divided by b is infinity, and then a plus b equals 6. The user still gets a real answer because 6 plus 0 is no problem at all. That last bare except deserves a closer look. With value error and the zero division error already handled, it is genuinely hard to name anything else that could fail here. Something drastic would have to happen. Perhaps the computer is nearly out of memory, and running this small program pushes it over the edge. The catch-all is a safety net for disasters you cannot predict, and in a healthy program, it should essentially never run. Two more blocks can attach to a try, and the first is else. An else block placed after the handlers runs only when everything inside the try block executed perfectly. Here, if both conversions and the division succeed, the program prints the result and then prints success. If any exception fires, the else is skipped. This is not the if-else you already know. Python reuses the keyword to mean success handling for a try. This class rarely uses it, but you should recognize it on sight. The second extra block is finally, and its rule is the simplest of all. A finally block runs no matter what. If an exception was raised, finally runs after the handler finishes. If everything worked without a single error, finally still runs. In this example, both the clean run and the broken run end by printing. This always runs. The classic use is cleanup. When a program opens files, they should be closed before it terminates, whether or not something crashed along the way, and finally is the place that guarantees it. Printing a message is not your only move. Inside an except block, you have three real options. Option 1, fail silently. Make the only line a pass and every error is swallowed. Nothing is flagged. And a potentially bad value keeps flowing through your program. Do not do this. At the very least, flag that something strange happened. Option 2, return an error flag value. Downstream code then must check that flag everywhere it matters, so the program fills up with extra variables and constant checking. Messy. Option 3, stop the execution deliberately on your own terms. That last option gets its own keyword. The keyword is raise. You name the error type you want and you put your own message in parentheses. Raise a value error with the message my own message. The program still crashes, and sometimes that is exactly right, because problematic code should not always be allowed to move on. But now it crashes with an error type you chose and the message you wrote, instead of whatever cryptic text Python would have produced on its own. Here is that idea in a working function. Some digits walks through a string, and for each character, C total increases by the integer value of C. Suppose we only ever want digits, and we refuse to pass along a total built from a corrupted string. The risky conversion sits inside a try, but the except no longer prints and carries on. It raises a value error with the message string contained a character. Feed the function a clean string of the digits 1 through 5, and there is no issue. The loop finishes and returns 15. Feed it a string with a letter buried in the middle, and it still crashes with a value error, the same exception type as before, but the message is now ours. String contained a character instead of the cryptic invalid literal complaint. Same crash are terms and words a human can read. Step back and the design is visible. Wrap unpredictable operations like user input in a try. Give every error you can anticipate its own named except block, and keep a bare catch-all at the end for the disasters you cannot. Reach for else when success deserves its own step, and finally when clean up must happen no matter what. And when a value is too broken to continue, do not fail silently and do not juggle flag values. Raise your own exception with your own message and crash on your own terms. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.